Okay, good morning. So this is where we stopped yesterday, right? That Bohr was trying to add structure to the electrons to fit them in with Rutherford's nuclear model of the atom. He looked at data from J.J. Balmer from the hydrogen line spectrum, and he corresponded that with specific orbits in the atom. And remember, if an electron falls from a higher orbit to a lower orbit, it gives off light, and the color of that light, the wavelength, is equal to the energy of the fall. So that's where we're at. So there's still a problem, of course, with Bohr's calculation. He figured out where the orbits would need to be for the different electrons, and then using regular old Newtonian physics that had been used for, like 300 years at that point, he was able to calculate the speed of the electron, just like we can calculate the speed of Earth versus the gravity of the sun, right? We can tell where the Earth would be in its orbit. When he did this, the electrons would have to be going like absurdly fast, like faster than they could possibly go, in order to stay out of the nucleus and in their own orbit. So Bohr is friends with a lot of physicists, as you could imagine. And he is talking about this problem with some of them. And one of them, Erwin Schrödinger, who you might have heard of in relation to Schrödinger's cat, takes Bohr's model of these orbits and tweaks it again. He keeps this idea that electrons are in different energy levels, right, farther away from the nucleus. But what Schrödinger said was that we can't know with certainty where an electron is in its orbit at any given time. We can only know with a certain probability. We can only guess where it is on a particular level. So this is the birth, this idea of Schrödinger's and others, is the birth of this new wave of physics called quantum mechanics. Until this time, we relied on Newtonian physics, where things were known exactly. If you knew, the speed of something and the time it had been traveling, you could know exactly where it was. You could pinpoint where the Earth would be around the sun, where all the planets would be around the sun at any given time. So quantum mechanics is like the antithesis of that. It's based entirely on probability. We can guess where an electron is located based on its energy, but we can't know exactly. And if you know the energy of an electron, you can't know its exact position. And part of the reason is that when you go to measure its exact position, you end up moving the electron. It's weird, basically. Quantum mechanics is awfully weird. So, in addition to Schrödinger and Bohr, we also have Werner Heisenberg. And Heisenberg looked at Bohr's model. He did some math. All of quantum mechanics is based on math. And what he did was he came up with these orbitals. So notice the word is different. It's orbital instead of just an orbit. That showed where an electron with a particular energy is likely to be 90% of the time. So, for instance, if you think about yourself being at school at a particular time, or yourself at a particular time, let's say right now it's 8:30. So let's say think about yourself at 8:30. On a normal weekday, you're likely to be in your first period class at 8:30 in the morning, but not all the time, right? Sometimes it might be a 3-2-1 day. It might be a late-in day. It might be a DLD. It might be a weekend. So we know where you're likely to be a lot of the time at 8:30, but that's not a guarantee that that is where you're going to be necessarily at that time. So what Heisenberg and Bohr and Schrodinger and others did was they did a whole bunch of math, and they set out and came up with 4 numbers called quantum numbers that sort of define where an electron is in that 90% of the time, like where it's likely to be most of the time. If you think back last year to biology, you may have done the little E lab. And that was the one where you had a big piece of paper, you rolled the dice 100 times, and you made dots on the paper based on where the dice, what the dice added up to. So you had 2. And so you ended up with sort of a map of a cloud of electrons, where what those values were the places the electron of hydrogen, just one electron of hydrogen, was likely to be. So where the electron was likely to be 90% of the time. So in the little E lab, you had the hydrogen nucleus, and then you should have at least gotten sort of a zone where most of the dots were, most of the electron probability was. And then there were these other zones where it was less likely that the electron would be there, but it still could be there. And that's kind of what we see in Heisenberg's orbitals as well. There's a zone of high probability for each electron, but there's other areas where the electron could be as well. So the quantum mechanical model of the atom is the newest model of the atom. It's the one that we use today. So electrons generally travel around the nucleus, in particular orbitals. So that is not the right word. Orbitals. And the key thing about quantum mechanics, you see, is that scientists can't predict where electrons will be at any given moment. Okay? They know that there are these areas of probability where the electron is likely to be 90% of the time, but that doesn't necessarily mean that that's where the electron is at the given moment when the scientists want to be looking at it. Those areas of probability make up what we think of now as the electron cloud. So it's a zone of high probability where a particular electron is likely to be found. So this idea that you could not know something exactly, right, that you couldn't know exactly where the electron would be at any given point, was a completely revolutionary idea. Until this time, remember that we were living in a Newtonian world where Isaac Newton could calculate, the orbits of the planets around the sun, the flight of a ball as it flies through the air, a spaceship. All these things rely on Newtonian physics, where we could know things exactly. And this idea of quantum mechanics, that we can't know exactly what an electron's going to do at any given point, just was completely different from that. Because there was a problem that couldn't be solved to an exact answer. It could only be solved to a probabilistic answer. Quantum mechanics has been extended to many other systems beside the atom. It tends to work for systems that are really small. But there are other things, like they think that birds flying, south or north for summer, winter, use some quantum mechanical properties in their brains potentially. Protein folding, they think, is done sort of quantumly. So it's been extended to many other systems beside the atom. And so it is quite a successful revolution. I'm going to post a video from Nova. It's a newer one than that one. So if you want to sort of learn more about this, I will post that. It's totally optional. But it's kind of cool if you're interested. So I'll post that. Here you can see a picture of the electron cloud. So here would be the probability for the innermost electrons, the first two, the second two electrons, and then the next 6 electrons are in those. So this is sort of what Schrödinger and Heisenberg and Bohr worked together on, was coming up with these graphical representations of the probability of the electron. So we'll talk more about this as we go. We are going to move into our big lab for the quarter soon when we get back to school. And in that, you're going to be looking at wavelengths of light produced from a variety of different atoms and using that sort of as a fingerprint to determine which atom is which element is which. So enjoy the rest of your day. Hopefully see you tomorrow.